have all been there. You spend days perfectly configuring your code, it runs flawlessly on your laptop, and the second you push it to a staging server, the entire application crashes. The culprit is almost always a mismatched environment, different operating systems, conflicting library versions, or missing dependencies. Docker solves this by packaging your application and its exact environment into a standardized unit called a container. To see how this works, we are going to break down the underlying mechanics and then use those principles to build and manage a custom Nginx web server. To execute this, you only need two components active on your system, the Docker engine running in the background and an open command line terminal. By mastering these commands, you stop treating servers as unpredictable variables. You become an architect who dictates the exact conditions under which your software runs. Before we write any commands, we need to understand how containers achieve this consistency. Historically, the solution to environment isolation was hardware virtualization. Today, we use OS-level containerization. The traditional virtual machine on the left requires an independent guest OS stacked on a hypervisor. Shift to the container model on the right. Containers share the host's OS kernel, communicating directly through the container engine, bypassing the need for a bulky hypervisor. This breaks down the client-server architecture. You interact with the Docker client, which translates your terminal command into a REST API request. It sends this to the Docker Daemon, the background process that pulls image blueprints from a Docker registry to build the container. By skipping the heavy virtualization layer entirely, applications boot up in milliseconds rather than minutes. Let's put that architecture to work. To launch our isolated Nginx web server, we start with the foundational command, docker run. If we execute that alone, the server will take over our terminal interface. We need to add the detached flag, a -d, forcing the container to run in the background, leaving our prompt free. Right now, our container is perfectly isolated and completely inaccessible. To breach this isolation, use the port mapping flag, -p, followed by 8080:80. This equation tells the Docker daemon to take port 8080 on your host machine and route any incoming traffic securely through the network barrier directly into port 80 inside the container. With the ports mapped, open your local web browser and navigate to localhost 8080. You will instantly see the default Nginx welcome screen confirming the server is live. Containers operate as sealed black boxes by design. Nothing gets in or out unless you explicitly authorize a mapped pathway. Once you have multiple applications running in the background, you need a way to monitor them. The Docker ps command outputs a table of all currently active containers on your system. Containers frequently spin up, execute a task, and shut down. To view the historical execution data, append the --all flag to that same command. If an application is failing, you need to read its internal output. Type Docker logs followed by the -f flag and the container ID, letting you watch the internal processes in real time. Sometimes reading logs isn't enough. You need to physically intervene. The Docker exec command allows you to run a new command inside a running container. Combine exec with the interactive terminal flag, -it, and specify a shell like sh. This detaches the command prompt from your local machine, dropping it into the container's isolated shell. You are now inside the environment. Run a standard list command, ls. You will not see your local documents, but rather a distinct, independent Linux file system. The runtime enforces strict boundaries for security and stability, but the CLI ensures you always maintain administrative oversight over the internal state. A container's internal file system is completely temporary and ephemeral. If the container is deleted, any data created inside it is lost along with it. To prevent data loss, we use Docker volumes. A volume is a dedicated, protected storage area on your host machine managed by Docker. The container reads and writes to this volume, ensuring your database records survive even if the container is destroyed. Volumes are best for persistent storage, but for active development, we use bind mounts. A bind mount maps a specific folder from your local laptop into the container, allowing you to edit source code locally and see the application update instantly. Moving beyond default setups requires building custom images. The foundation is the Dockerfile, a reproducible, line-by-line text blueprint defining how your application is assembled. When you build an image, Docker processes it in layers. Each instruction in your text file generates a distinct, read-only structural tier. If you change one line of code, Docker only rebuilds that specific layer, making the build process highly efficient. You can also use the Dockerfile to inject dynamic configuration variables using the env instruction. This lets you pass API keys at runtime without hard-coding sensitive info into your application logic. A resilient architecture keeps its permanent data safely stored in volumes, encodes configuration in text blueprints, and treats the running container as a strictly disposable execution layer. We have pulled a public image, mapped network ports, secured our data with volumes, and traced the mechanics of custom, layered Docker files. You no longer have to hope your application runs cleanly on a new server. You now possess the tools to package immutable infrastructure and deploy it with consistent, predictable results. Managing one container perfectly is the critical first step. The next stage is scaling this control, moving from single instances to orchestrating entire networks of interconnected microservices.
And structured path for class.